Hi class, welcome to Refrigeration and Air Conditioning, lecture number 11. Today we'll study about vapor compression refrigeration cycles. In the previous lectures we had looked at Carnot cycle and Brayton cycle, the refrigeration cycles, and today we'll analyze the vapor compression cycle using coolprop. So as you already know, in this cycle there is phase change. Okay, so the refrigerant undergoes phase change from liquid to vapor and from vapor to liquid. The ideal processes in this particular ideal vapor compression cycle are the isentropic compression, isobaric heat transfer for the high side and low side. And what I mean is high temperature and low temperature isobaric heat transfer. And the expansion process is isenthalpic instead of isentropic. Okay, so that's a big difference from these two. In all of these cases, the expansion process was isentropic. Here it is isenthalpic. This is a very efficient system. It is usually much better than the air cycle. However, it is of course not as good as the Carnot cycle, which is an idealistic cycle, which is not possible in reality, right? The vapor compression cycle is widely used, though not the ideal one, but the actual vapor compression cycle, which has non-ideal processes, is the most widely used refrigeration mechanism across all industries throughout the world. Okay. All right. So let's start with going back to the Carnot refrigeration cycle, and we'll try to apply it to a two-phase scenario and see why it won't work. In a typical gas cycle like reverse Brayton cycle, the working fluid is gas and there's no phase change. So if we draw the TS diagram for gases, this is all, there's no phase change diagram in here. Their phase change occurs way far away in lower entropies um, compared to where they normally operate. Okay. On the other hand, with refrigerants that undergo phase change under typical conditions, the Carnot cycle may be inside the two-phase region, like this, for example. Okay. Now, what is the problem with that? And before we get into that, um, let's try to understand one more thing about the TS diagram. So if this was a Carnot refrigeration cycle, and you wanted to understand what is the Q going into the lower side and the Q leaving from the higher side or high temperature side, what you would do is you basically integrate on the TS diagram. You know that delta or ds is delta Q reversible over T. You know the classical definition of entropy, right? So if you integrate TdS, right? Integrate TdS is nothing but Q reversible, total Q that has been work done that is reversible. But in reality, if this is not a reversible process, the ds would be typically greater than this value, right? So anyway, this, if you integrate and assume it's a reversible process, this area represents, so if you have a TS diagram, and if you have any process 1 to 2, the area under that process basically represents the heat that is transferred during that process. Okay, so basically this is Q. So in this case, from 4 to 1, which is this process, this represents the QE that is absorbed, QE, right? Integral, that value. For 2 to 3, it represents the overall QC, okay, that has been transferred. So if you take the area from let me change the color here. So uh, this green color represents QC, okay? Um, the net heat that is going out. And what is represented by the area inside? Um, so let's use a blue. So the area inside is basically QC minus QE, which is the net work. This represents net work. So the area enclosed within the process 1, 2, 3, 4 is the net work that is coming out, which is equal to QC minus QE. Okay, so remember that about TDS diagrams. And the assumption here is the Q is the process is reversible. Like the process 4 to 1 is happening reversibly. These are not isentropic processes, like 4 to 1 is not isentropic, but it could be a non-isentropic process but reversible. Okay. So his assumption is it's happening without a lot of friction. It's happening without um, uh, it's happening in such a slow manner that it's always in equilibrium. So it's a really slow process without a lot of friction. Okay, that's what that means. Okay, so let's do some analysis here and try to calculate Carnot efficiency and the work done during a Carnot refrigeration cycle using CoolProp. So open the VCR cycle Excel file and go to Carnot efficiency gas and Carnot refrigeration vapor, both of them. Okay. So for the gas scenario, we could basically calculate using three different methods. One is we'll use the ideal gas equations and the work done on ideal gas that we have derived in the previous class. We can use that and also use the same thing for measuring the QH and QL, which is same as the QE and QC we are looking at. So QH, QL, W, you could calculate it for certain ideal gas, in this case oxygen, um, and you get a number of 5.295 for the conditions we are using here. We're using a low temperature of -10 and a high temperature of 40 degrees C. Okay, so each state point 1, 2, and 3 and 4 are calculated for pH diagram, TS diagram, PV diagram here, and you can see, for example, uh, the TS diagram looks exactly like the TS diagram we have below, and the PV diagram also looks very similar to the PV diagram below, right? Um, so let's look at another way to calculate, which is based on the entropy area that I was telling you. So you could calculate using the area under the entropy curve. Um, so if you look at the TS diagram, okay, the QH is a heat transfer at the high temperature is basically S3 minus S2 times T2, okay? So times the temperature that's happening at. So the temperature is T2 equal to T3. So you get a certain QH and a certain QL the same way here. And W is just the area inside this rectangle. You calculate W, and once you have W, you calculate 5.263 based on Q over W. Okay, um, basically QL over W, because QL is the amount of heat you're removing. Okay, so if you look at it, it's QL over W. Um, Now you could also calculate using the Carnot temperature formula. So in this case, T um, low is T1 and T high is T3, or same as T2. So you could use the Carnot efficiency formula and you get the same number. So only number that's slightly off is the ideal gas number assumption. If you probably put helium, which is more of an ideal gas, instead of air, um, you'll get a closer number here, right? Now you're closer to the same COP as before. So far what we've done is basically calculating the COP for a Carnot cycle for gas. What if the working fluid is a vapor which can change phases? In that case, we cannot use this particular formula because this formula is used for ideal gases. We could calculate the same using the other two methods, the area of under the TS diagram and also the two temperature method. Okay, so here we are doing R1, we are using R134A, and we are calculating the properties for a TS diagram, and it's most likely inside the vapor dome like this. Okay, so it usually doesn't matter where you are. Um, the Carnot cycle is ideal. It can operate here, it could operate here like this, it could operate anywhere because it's just a idealized cycle. You will still get the results based on the high and low temperatures. Okay, all right. So you can see that both methods that you calculate, um, your COP is the same, and you can easily estimate the W using the TS diagram. Okay, let's go back to our lecture. Now, we looked at the Carnot refrigeration cycle, and what we just explained, uh, of course, will not happen in a in practical scenario because Carnot cycle has um, several ideal processes like isentropic com compression and expansion. Those things are not very practical anyway. In addition to that, if you're considering a vapor cycle inside a two-phase dome like this, um, it is hard to um, it's hard to make it practical due to another problem, which is you cannot design a compressor to compress liquids or mixtures. Okay, compressors are meant for dry compression for gases. So you cannot have the compression process 1 to 2 inside the vapor dome. You have to move the process 1 to 2 outside the dome, okay? Because imagine you have a compressor and you're trying to compress liquid, okay? It's meant for compressing gases. The liquids will not compress and it will damage the piston, damage the valves, it will damage the whole system. And sometimes if you have air conditioners in your house, sometimes you'll hear really loud noise coming from the compressor outside your house. And a lot of times it's due to liquid getting in to the compression chamber and a little bit of liquid getting into your system, and that is creating a lot of compression issues, a lot of vibrations. And if too much liquid gets in, it could damage the mechanical components of a compressor. So it's not practical to have a compressor that is trying to compress liquid or a liquid vapor mixture. So you need to do the compression outside this dome. Now, 3 to 4 is turbine, right? We have seen air turbine in the air cycle refrigeration, but that was air cycle, okay, and that turbine was driving the compressor. It's not really practical for a vapor compression system to use turbine, primarily because it's hard to extract work. There is not enough work that could be extracted and used for compression, okay? Because the amount of work that you extract is only probably less than 5% needed to do the compression in such systems. In an air cycle refrigeration system, you saw this because you had two compressors there. One is the actual engine of the aircraft. So you had compressed air already coming in and you need a little bit more compression. Here, all the compression is done here, right? So there's not any meaningful energy that you can extract to support the compressor. So typically it is not very beneficial for the cost and complexity you would add in such a system. And the reason for not enough energy you can extract out of it is because of the lower flow rates compared to an air cycle refrigeration system. And again, two-phase flow regime makes the turbine option not so great either. It'll damage the turbine. It could be an unsteady rotation of the turbine, and it's not very feasible to extract work. So because of uh, these two processes, process 1, 2, and sorry, this process is 3, 4. Because of these two processes, uh, Carnot vapor cycle is really not practical. So how do we create a an actual vapor compression cycle? Now, to solve the two practical issues mentioned, um, what we could do is for the process 1, 2, we change that process, move that process to be outside the dome. By the way, this is a TS diagram. Um, Move that process outside the dome, and then we replace it with one isentropic compression. Okay, that'll compress it into the gas phase, and then from that intermediate pressure, you have to take it to the condition next to the dome, so that you will use an isothermal compression. Okay, so constant T here because it's a TS diagram. And if you have a TS diagram and you have a two-phase dome, you know that the isobaric lines, sorry, isobaric lines are somewhat like this. Okay, um, so they are constant here, like P equal to constant here lines. The T equal to also constant here inside the two-phase region. And then the temperature increases in the vapor region with pressure, just like an ideal gas. So if you try to compress outside, you'll get to a pressure, um, but you're not able to go turn left without doing an isothermal compression. So you go to another higher pressure, so this P2 is greater than this P1. So you're doing compression in both these cases, okay? One is isothermal and one is isentropic. So once you do that, and then you do the high temperature heat loss in the condenser, which is QC, okay? So 3 to 4 is QC. And then 4 to 5, instead of the turbine and the issues that we talked about before, uh, we do um, a isenthalpy expansion with a throttling device. Okay, so there is no turbine. This is a Joule-Thomson type expansion with a throttling device, isenthalpic, and you have done calculations on this in the previous lectures. Okay, so the shape now becomes something like this. This is our new process, right? This is one way to solve this. However, this is not practical again because it is expensive to have two compressors and it's not practical to achieve isothermal compression. That's really hard. So what is the actual solution? So the two compressor problem is solved and the actual ideal vapor compression cycle is derived using this method here. So instead of using two compressors, we have one compressor and we are operating between, again, these two temperatures. But there is another temperature here. We can call it, for example, discharge temperature, okay? So that's actually the highest temperature in this diagram. So you actually go higher than the um, actual condenser temperature and then come down to actual condensing temperature. So what does that mean? So what that means is you're still doing isentropic compression with one compressor, okay? Um, but you compress a little bit more. You compress a little bit more to get to the pressure that you want for your condensing side, right? And once you get to that pressure, you drop temperature by doing heat transfer to the outside. So in this case, all of that could happen inside the condenser. Okay, so you have a constant pressure heat loss process, but it's not a constant temperature. You are dropping temperature initially, and then you reach the two-phase dome, and then you have constant temperature and pressure. Okay, and the rest of it is same as what we discussed before. We have isenthalpic expansion, and then um, isothermal heat removal and isentropic compression. So let's look at all these processes in detail. So process 1 to 2, compressed isentropically to a really high temperature in the compressor. Okay, this is the hottest point, and we usually call it as the discharge temperature of the compressor. That's the hottest temperature in your system. And that temperature is cooled to temperature 3, which is basically usually referred to as the condenser temperature. Okay, so condenser in temperature could be somewhere between 2 and 2 prime, uh, like T2 and T2 prime if you look at the temperature axis here. Sometimes it's very close to T2, sometimes it's closer to T2 prime, depending on how much heat you lose in the lines that take the compressor fluid to the condenser. Okay, and then the expansion, again, it's a throttling type device. You'll have an isenthalpic expansion. It's not isentropic. Isentropic would be straight line here, and that happens at 3-4. Okay, so high pressure liquid refrigerant is expanded isentropically through expansion valve. Let's go back here one more step. Here it is gas. Okay, it's coming into the condenser as gas. Somewhere in the middle of the condenser, it starts forming liquid. Okay, so it doesn't have liquid in the beginning of the condenser. It gets colder, right? The temperature drops and reaches the two-phase region and starts forming liquid. So somewhere here it starts forming liquid, and by the time it comes out, it's based on the ideal cycle, it's all liquid that's going to the expansion device. Then outside of the expansion device, it's again liquid plus vapor. And the remaining one goes to the evaporator. The remaining liquid evaporates, and by the time it finishes here, or by the time it reaches here, it's all vapor again. Okay, so it's vapor here and goes to the compressor. So this way we solve the practical issue of compressing um, a liquid or a liquid vapor mixture by putting the compressor here, and also solve the issue of having two compressors by compressing it to a higher temperature and dropping it in temperature, and then um, expanding it later through a throttling device. So in a TS diagram, an ideal refrigeration cycle would look something like this. Okay, this shape. Um, the PV diagram looks something like this. 1 to 2, the pressure increases, volume decreases due to compression. 2 to 3, 2 to 3, there is no change in pressure. This is isentropic pressure line. And I think I made a mistake here. This line should go down like this. It shouldn't go like that. Isentropic pressure lines go like this on a TS diagram. Okay. So 2 to 3 is constant pressure, 3 to 4 is the expansion in isenthalpic process, 4 to 1 is again um, evaporation at constant pressure. So there are two isobaric processes, one isentropic and one isenthalpic. So because of two constant pressure and one constant enthalpy process, vapor compression cycles are typically represented on a pH diagram, because there's two pressure high, pressure low, right? Two processes that are pressure related, and another process that is enthalpy related, H equal to constant here. This is isentropic, but it could be still represented on a pH diagram, right? So pH diagram is the most commonly used diagram in industry for analyzing vapor compression systems. Okay, just because it's easier to understand and it's easier to calculate cooling capacity and all by just looking at the enthalpy. All right. Now let's try to figure out the two effects that we modified or the two changes that we made onto the Carnot cycle to develop the ideal VCRS cycle. How do they affect the efficiency? So the first one is the isenthalpic expansion or throttling. So if you want to first estimate the effect of throttling on the overall efficiency, let's look at the effect on the cooling capacity. Uh, Cooling capacity is the amount of heat that you're able to remove here, the QL, right, uh, from 4 to 1. And you're taking that heat and leaving it outside to the ambient at QH, okay? And then you have there, you're putting some work in here, which is basically the area inside. So if you look at QL Carnot, um, Carnot cycle is the full rectangle here. 1, 2, double prime, 3, 4 prime, 1. So this rectangle, that's the Carnot cycle. Now, for Carnot cycle, the QL is basically area under 4 prime to 1. So C 4 prime 1 E, right? C 4 prime 1 E C, back to C. So that area is the uh, amount of Q that the Carnot cycle can remove. For the VCRS, it starts from 4 to 1. It's actually 4 to 1. So it's D41ED. Okay. So that's a smaller area. So the amount of heat removed in the VCR cycle is less than the amount of heat removed in the Carnot cycle by this much, by this area noted here. Okay. So it's always going to be less heat removed. That's because the expansion brings the refrigerant at position 4 prime versus 4. So you're losing some cooling capacity. Okay. Now, work done. Net work done is the area enclosed between the processes of the two heat transfers. Okay. So for Carnot, it is basically the area inside the rectangle. So it is basically 1, 2 double prime, 3, 4 prime, 1. For the VCRS, you have to find the area enclosed by this cycle first, which is the QH, and subtract it from this cycle, which is the smaller rectangle here. When you subtract that, you'll get these two additional areas on top of the Carnot area. So you will have to do extra work in vapor compression cycle compared to Carnot. So overall, the efficiency is decreased by lower cooling effect, which is caused by QL minus A2, and um, higher work. Okay, so efficiency is lower. So if you can make these two areas smaller, you can probably get it closer to a Carnot cycle. Okay, and the biggest impact is the area A2 because it comes in both the numerator and the denominator, right? It's hurting in both cases. It's reducing the cooling efficiency and it's also making you do more work in the compressor. All right. Now, um, let's do the same analysis using a pH diagram instead of a TS diagram. Okay, so in the pH diagram, the QL or the heat transfer happening at the lower temperature in the evaporator is from process 4 to 1. 4 to 1. Okay, so you're going left to right. So that's the process 4 to 1. And how do we calculate the um, energy transfer. The energy transfer here, QL, is also known as the um, change in enthalpy from this point to this point. Okay, it's H4 minus H1, or ideally it's H1 minus H4. Okay, H4 minus H1 will give you a negative number, but it's the amount of heat removed. Cooling rate is basically, so this is in joules per kilogram. If you multiply that with the mass flow rate, if you know how fast is the refrigerant moving through the system, and the mass flow rate at steady state, it will be constant everywhere in the system. Okay, so mass flow rate is multiplied with the change in enthalpy to get the actual cooling rate in watts. Okay, now heat transfer at condenser, uh, or the heat rejection, is basically between 2 and 3. So you find the enthalpy between these two and multiply it with the mass to get the heat rejection rate in watts. Expansion process, the assumption is isenthalpic, right? H equal to constant. So you'll have the same H at 4 that you got at 3. Okay, so assume it's the same H, but the pressure drops. Now, work done by the compressor, you can calculate from enthalpy change between 1 and 2, H2 minus H1. And typically, the assumption is it's isentropic. Okay, so rate of work done is, again, you multiply mass with that change in enthalpy. The COP of such a system is basically QL divided by work done. So it will be QL is H1 minus H4 divided by H2 minus H1. Okay, so um, that is the COP in terms of enthalpy. And these are the temperatures. T1 and T4 are same as evap temperature, and T3 and T2 prime are basically the condenser temperature. T2 is not same as T2 prime, okay? T2 is discharge temperature. You know that T2 is much higher. So we will not use T2 in our calculations. The evaporator pressure is the uh, saturation pressure corresponding to the temperature TE. Okay, so you already know what is saturation pressure. So the pressure here is related to the temperature here, TC. Okay, they are saturation pressure and temperatures because they are inside the vapor dome, right? So the pressure and temperature are a function of each other. And the same thing goes for both the pressures, the evaporator and the condenser pressure. Okay, now let's look at how to construct a full VCRS cycle if we know the temperatures of the high and the low sides. This is basically the TH and this is basically the TL. It's called the condensing and the evaporating temperatures. If we know these two temperatures, we can easily calculate PC and PE, right? Um, you assume that that's the saturation pressure, okay, and you can easily calculate PC and PE. So you basically know, if you know these two things, the TC and TE, you know PC and PE for a given refrigerant, okay? So you can do that with cool props. So in cool props, for example, you would basically input the TC value and a Q value in between 0 to 1, and you'll get the P saturation, right? So the same way for TE, you can put P saturation. In this case, if you input TC, you get PC. If you input TE, you'll get PE. Now, how to calculate the x-axis values? So if you know the TC and PC values for state 3 here, you know that on this line here, okay, the quality is 1 here and the quality is 0 here. So you choose quality equal to 0 there and calculate H3. And once you have H3, you already know H4 because H3 and H4 are the same. right? So you started with TC and TE and you calculated um, H4 and H3. Okay, so you know this point because you know the PC, you know P3 and H3. Okay, you also know PE and H4. So you know these two locations. So you created these two. Now, how do you know the location one? You know the PE value, but you don't know what is the enthalpy there. So to calculate H1, we have to assume that it's on the vapor dome at quality equal to 1. So use TE or PE and a quality of 1 and estimate H1. So now you know this point. So you have calculated these 3 points. Now you want to calculate this point. So for that, you assume isentropic compression, right? S equal to constant on here. So first calculate the S value here and assume that is the same value here. S1 is same as S2. And you also know the pressure here, right? Um, so so you can calculate the H2 at this point using the pressure here, which is PC. Okay, PC is here. So now you know this point too. So if that way you have calculated all the points in the cycle for an ideal VCRS if you are given the two temperatures. The same way you could do this if you are given the two pressures. So anytime somebody tells you that I want to calculate the ideal VCRS properties for this refrigerant, all the only information you need from them is either the two pressures in which they want to operate or the two temperatures in which they want to operate. And you can calculate that for any refrigerant, right? Um, it's easy to plot. So let's look at how to do this using CoolProp. So open your Excel file and go to the ideal VCRS tab. Here I've created the pH diagram, TS diagram, and PV diagram for the for any refrigerant that you want to choose here, right? And I've created the 4 points, 1, 2, 3, and 4, just like in these diagrams. So you can refer to this diagram when you're looking here, okay? Um, so the only input that you need is the lower and the higher temperatures, the compressor, sorry, the evaporator and the condenser temperatures, okay? T1 and T3. You can see that T2 is usually warmer than T3 because T2 is here, T3 is here. T2 is much hotter than T3. Okay. Um, what will happen if we change some of these values? Let's try. Oh, before that, what else is this calculating? It's also calculating the QH, QL, W, and the COP. It's using enthalpy formulations to do these calculations. If you know the mass flow rate of the refrigerant, you can actually calculate the watts of work done, um, the heat removed and everything. You multiply the mass flow rate in kilograms per second with these numbers and you'll get those things. Here, the COP for this particular case is calculated to be this value and the Carnot efficiency is calculated to be much higher. So the Carnot efficiency is several percentage better than the VCRS. VCRS is only 76% of the Carnot efficiency. Okay, that's because, of course, of the two things we already mentioned: the vapor dome, sorry, the vapor horn here, and the throttling losses. Right. You can also see how well these plots match with the actual plots from the textbooks. Right. Um, you can see that this kind of traces this type of chart really well. This also mirrors the this plot here and the same thing here, right? So play with these numbers, keep changing these numbers and see how the efficiency changes. You can also put in a different refrigerant like R600A, for example, and see how the efficiency changes. So when I went from R134A to R600A, the efficiency number here changed, right? So it's a different dome shape for different refrigerants. So for between the same temperatures, different refrigerants will give you different um, efficiencies because it all depends on where you are on that dome. And if the shape of the dome changes, then the shape of your um, plot changes and it changes your efficiency. Just pay attention here. So for R608 it is 4.113, and if I change it to R134A, it probably should decrease. Yes, it decreases to a lower efficiency. So typically R600A is considered to be a better, if more efficient refrigerant, right? Because of the shape of its dome. So sometimes refrigerant selection is also important for energy efficiency. All right. Now let's try to understand the effect of condensing temperatures and evaporator temperatures using CoolProp. The efficiency, if you remember the Carnot refrigeration efficiency, it decreases. It decreases with the increase in high temperature, and it increases with the increase in low temperature. The same thing here. So with low temperature, the efficiency increases, COP increases. For different high temperature scenarios, as the high temperature um, goes increases, the efficiency decreases. Okay, so let's plot that using CoolProp and verify. Go to this chart, and here we have changed the evap temperatures T1 from -40 to 20 and kept the condensing temperature constant. We calculate the efficiency for both Carnot and the VCR cycle. Okay, so you can see. Um, so what we are doing is we are creating several of these um, plots and calculating them for each combination. And you can do that by just taking the ratio of enthalpies, right? So as the lower temperature increases, the efficiency increases significantly. So if you have a refrigerator operating at an evap temperature of -20 degrees C, it'll be consuming more electricity than if you are able to adjust it and make it operate at, let's say, -15 degrees. Um, so a warmer evaporator typically is considered more beneficial in terms of energy efficiency. Now, about the condensing temperature, it's the opposite. It goes down. So higher the condensing temperature, the lower the efficiency. And you can see that both for the VCR cycle and the Carnot cycle. All right. Now, in a real vapor compression cycle, okay, these are ideal. Why are they ideal? Um, there are several reasons. One of them is the processes involved are ideal processes. You have isentropic compression, you have isenthalpic expansion, all that. Those are not real. Um, Even the constant pressure process is not real. You have some pressure drop here, some pressure drop here too. But one of the first things that um, deviates from real process, from ideal process to real process is it may not be exactly coming in at um, the phase change line. It might go a little bit towards the left. Okay, so it might be doing a little bit of subcooling. So you're not in the exact vapor liquid equilibrium, you are fully liquid. And when you're fully liquid, it's called subcooled state. Okay, you're not at the saturation state, you're at the subcooled state. So you could be a little bit colder before coming into the expansion device. Okay, so instead of coming in at 3 prime, you're coming in at 3. Okay, so instead of, what does that mean really? If you're coming in at 3 prime, that means you have some vapor in that liquid, okay, because it's not Q equal to 0. If you're coming in at 3, that means Q is 0. What I mean by Q is the quality. So it's fully liquid when you're coming in here. So when you have subcooling, it's all liquid going to the expansion device. How does that affect the the system? This is actually a good thing for the system. If you can subcool it, you will expand and come out at 4, and from 4 to 1 you have a bigger cooling effect. Okay, so your cooling effect increases. All right, so COP of VCRS subcooled is the differences from H1 to H4 divided by H2 minus H1. For ideal is H1 to H4 prime, so you have less cooling effect. So subcooling improves COP by increasing the cooling capacity. Okay, increases cooling capacity. So cooling capacity increases by this much. So this plus this. Okay, so you get this total cooling capacity if you're coming in here in the evaporator. Okay, so you have more liquid in the evaporator as opposed to less liquid in the evaporator, and you can boil more liquid or evaporate more liquid, and because of that you can cool more. So your cooling capacity is increased. Now let's consider what happens at the exit of the evaporator at location 1. Okay, so in an ideal Carnot cycle, the exit of the evaporator looks somewhat like this. You're exactly at this region where there is still some two-phase, right? And after that, it becomes single phase by the time it reaches compressor. Now, what if the exit of the evaporator is here? That means it became single phase inside the evaporator. Okay, and once it's single phase, its temperature will not be constant anymore. Okay, so when you're here, basically you are at a different temperature than when you're over here. So if you remember how the temperature lines, isothermal lines, behave on a pH diagram, um, so if you have a pH diagram like this, the isothermal lines follow some path like this, right? So if you are here and you move to the right, you're hitting a higher temperature line, okay? So there'll be a lot of lines like that. So the moment you move towards the right past the vapor dome here, you start increasing in temperature. So it's going to be at a higher temperature here, okay? Um, but of course, there's higher enthalpy also corresponding to that. So you're basically coming in at a constant evap temperature, okay, up till here, and then your temperature increases by a small amount. And that small amount is called the superheat, which is called superheating. So you're heating a little bit more. Now, what effect does this have on the overall cycle? And majority of the systems always have a little bit of superheat. Okay. So what happens is if you try to calculate the COP of the superheated condition, QL over WHC, you basically are H1 to H4 in terms of cooling effect. Okay. Assuming that uh, the heating of the evaporator is used for cooling your system or cooling whatever you're trying to cool, then you could use the whole left to right here as the cooling load. So H1 minus H4, and then the input is the workload, which is H2 minus H1, the compressor load, okay? For the ideal scenario, it is H1 prime minus H4 because you're coming out here in the evaporator and you're coming in here in the evaporator. So enthalpy difference is this much. And the work done in the compressor is also different here. So which one is better? It's hard to know this because typically increasing the superheat increases the cooling capacity. However, as you go towards more and more vapor at higher temperature, you need to spend more amount of work in the compressor to achieve the same um, conditions in the evaporator and condenser, right? So what happens is there is an optimal superheat value, um, after which if you keep on increasing the superheat, it will decrease the COP. So if you had to plot between COP and superheat, so it will keep on increasing and reach an optimal and then it start dropping. Okay, so you do zero superheat is not the optimal. Okay, and maximum superheat is also not the optimal, somewhere in the middle. All right. So let's analyze both this subcooling and superheat effect um, using CoolProp. Okay. All right. So let's go here and go to actual VCRS, right? And leave the isentropic compressor efficiency as 1. Okay. Don't change that yet. We haven't done that portion yet. But here I'm showing you the uh, the differences, subcooling and superheating. Okay, so 1 prime to 1 is the superheat, 4 prime to 4 is the subcool, or 3 prime to 3 is the subcooling. So here is the amount of subcooling and superheating values that you can put. For now, I'm going to put them to a really low value. Don't put them as 0, it will give an error here because of the way the calculation is set up. You can put it at a really low value. Make sure you put the isentropic efficiency of the compressor at 1, and we'll change that later. So minus 10 and 40 for R134A, you're getting the same efficiency that you saw in an ideal VCRS. So if you have an ideal VCRS, um, minus 10 and 40, you'll get very close to the value that I just showed you, 4.029. Okay, actual VCRS. So maybe we take this even lower. So it'll become, so now the values are identical, 4.029 here and 4.029 here in ideal and the actual. So now if you add some superheat, add some subcooling, okay, so if I made it 10 or made it 5, so 5 degrees of subcooling, you will see that 3 prime and 3, they've separated now. So if it was 0.001, they're identically on top of each other. Okay. I don't know why this one is not moving yet, but ideally they're right on top of each other. Um, so if you change that to 5 or 10, you'll see them move. Okay. Now we have separated the 3 prime from 3. Okay. So now you could see that the efficiency has increased. It was 4.029, now it became 4.249. So subcooling is increasing efficiency. Let's go back and try to put superheating and see what happens at 1 prime and 1. So if I put 5 degrees superheat, you can see the 1 prime and 1 changed, and the 2 prime and 2 also changed. Okay, so what did it do to the efficiency to increase the efficiency? It went from 4.029 to 4.048. Now let's try increasing it a lot to 10 Kelvin. It's still increasing. Okay, now let's probably increase it quite a lot, 25 Kelvin. It's still increasing. At some point, it will stop increasing in terms of superheat. Now let's revisit another assumption in the ideal VCRs, which is isentropic compression. In real VCRs, the compression is not isentropic, right? So typically what is done, especially during modeling, is we assume a percentage of efficiency to isentropic. So isentropic efficiency is basically Uh, Assumption is you have isentropic work done, so you calculate the um, enthalpy here, assuming an isentropic process. Okay, enthalpy at 2 at the discharge of the compressor. So you would calculate the work done as this for an isentropic compression. Now, the real assumption here is that you need to do more work than isentropic to do compression in a real system. There is more nuance to this. This is a confusing aspect. I'm not going to the details of it. I'm going to teach you the way most of the academics is tailored to. Um, so the assumption here is it will come out at a much higher temperature in a real process when compared to isentropic. It's not always true. There are some nuances here. I will. It's probably beyond the scope of this lecture, but for now, assume that if you do a real process, you will always go to the right side and above the discharge temperatures that will be seen in an isentropic process. So in that case, the work done is H2 minus H1. The ratio of this isentropic work to actual work done in the compressor uh, is the isentropic efficiency. Okay, so if you say 75 to 85% efficient, that means you have to multiply that much more to the isentropic work to estimate the amount of work you will do in your real system. Okay, so let's go back to our cool prop and change this variable. So I've changed everything back to 4.03 here. Now change this to 0.85, for example, 85%. So you could see now that the the two numbers have split. Um, it it represents the change between 2s and 2 here. Okay, so that creates a drop, a big drop in efficiency from isentropic to non-isentropic compression. Okay, so typically the best compression is assumed to be isentropic, but that's not really true. If you could actually lose heat while compressing, that's the best way to compress. Isentropic compression means there's no way to lose heat, uh, but it is typically used for analyzing any system. It gives you a reference point. It makes modeling easy if you assume a percentage over isentropic compression to be your actual compression. Okay. All right. So now one last thing is the liquid suction heat exchanger. This is another way in which most refrigeration systems differ from the actual vapor compression system. The reason for having a liquid suction heat exchanger is we noticed that when we had a little bit of subcooling, our efficiency improved. And when we have a little bit of superheating, our efficiency improved. Let's go back to that and look at it one more time. So when you had no subcooling or superheating, the efficiency is 4.03. Okay. Um, Let me split this screen. Um, okay. So let's split this screen so you don't have to go back and forth. Okay. So pay attention to this cell here. Now if I change the superheat to 5 degrees, the efficiency increased from 4.03 to 4.048. Now if I increase the subcooling, also efficiency increased further, right? So what if we use one portion of our system which is hot to to heat another portion of the system? So you are getting subcooling and superheating due to a heat exchanger. So that's exactly what this is. So if you're able to get some superheat here, okay, delta superheat, and get some subcooling here, and you're basically exchanging heat within yourself in your system, okay? Instead of doing that from an external source, uh, it is going to help you with your efficiency, right? So that's what that is. It is usually called a liquid suction heat exchanger. So the term suction comes because it's on the suction side of the compressor. Okay, it's right before compressor. So a lot of times anything that's going into the compressor we refer to as suction. Anything that is coming out of the compressor we refer to as discharge. So suction line is exchanging heat with the liquid line coming from the condenser. Okay, and it cools down like this. It cools down like this. So you get some extra cooling effect here, and then it heats this portion a little bit. So overall, you're benefiting primarily from subcooling. Okay, the amount of heat that is being transferred between these two depends on the efficiency of the suction line heat exchanger. Okay, and typically it's represented by this number. Um, so suction line heater efficiency is T1 minus T1 prime. How much temperature can change here versus T3 prime minus T1 prime. Okay, so the ratio of actual heat transfer rate to the maximum possible heat transfer rate. Um, so this efficiency um, is usually less than 1. So we'll see how suction line heat exchanger affects your system using a cool prop calculation. So go to the actual VCR cycle with suction line heat exchanger, um, and let's view with split screen. Okay, so here you have the heat exchanger efficiency, effectiveness. Um, if you have almost zero effectiveness, 0.001, that means there is no subcooling and superheating. Okay, um, so actual superheat is really small for that. Let me reduce it further. So if you make this really low number, you'll get very little supercooling and uh, superheating and subcooling. Okay. If you increase this number, you get very high heat exchange between um, the superheat side and the subcooling side. So if you have this number here, you're basically very close to the 4.029 value we have been seeing so far. And now if you increase the heat exchanger effectiveness, um, make it zero point 0.5, for example, and let's pay attention to what happens to the yellow cells here. So there's a big change in temperatures if the heat exchanger effectiveness changes, right? So if you have a good heat exchanger, there's a lot of superheat and a good amount of subcooling. And you have increased your COP, okay, because of that. So um, every refrigerator in the market, every air conditioner, they all try to exchange some form of heat internally to make use of the benefits of um, having extra cooling effect because you're coming in further to the left here, right? If you had come primarily the benefit is coming from the extra cooling effect. If you had landed here, you have only this much cooling effect. If you're landing here, you have an additional amount of cooling effect. So if you can cool your liquid line before it comes into the expansion valve, or sometimes you're instead of having the cooling here, you'll have a heat exchanger here. Okay, it is usually called capillary suction line heat exchanger. So you can do a heat exchanger here or here, whichever way you cool it, and you bring bring it further towards the left such that more liquid comes to the evaporator, you're increasing the cooling capacity of the evaporator. And that is always done in all the commercial refrigerators and air conditioners to gain this free efficiency. Okay, you don't have to do extra work. You just have to add a heat exchanger, and you can reap the benefits from that. Okay, all right. So that concludes this lecture on vapor compression cycles. We had looked at the ideal and actual vapor compression cycle to a certain extent. We are primarily analyzing them using the two-phase diagrams, but you can actually measure the wattage or calculate the wattage by using a mass flow rate. If you know the mass flow rate, you can multiply that with any of these numbers like QH, QL, or W to calculate the actual capacities and the actual work done in a real system. All right, thank you.